In our class, we've been talking about intermolecular forces. That's the forces between molecules. And now what we're going to do is connect those to physical properties, that is the way things behave. So we're going to look at surface tension, adhesion, and cohesion in this lesson. And in the next lesson, we'll look at some other physical properties and how they relate to intermolecular forces. Okay, let's start with a question. Why are water droplets round? Now, on Earth, gravity pulls water droplets so that they're sort of teardrop shaped. But if you go out in space and you look at a water droplet, that's where this photograph was taken, it's perfectly round. Why is that? Well, why isn't, for example, it a cube or a pyramid, but it prefers a sphere? Why does water care? Well, it has to do with our intermolecular forces and one other thing. So let me give you a hint right off the bat as to why it's round. And that is that spheres minimize surface area. So that's the shape that minimizes surface area. What that means is that if I took that same amount of water and I made it into, say, a cube or a pyramid, there would be more surface area. So spheres minimize surface area, and that's a really important part of the answer. The other part of the answer that's important is cohesive forces. Cohesive forces are attractive forces within a substance. Basically, there's no difference between an intermolecular force and a cohesive force. We're just saying, hey, all of these intermolecular forces we have hold together our molecules and they would like to be together. So water would like to be near other water. And we can understand that at a molecular scale if we remember that our water, with its 2 hydrogens and 1 oxygen, is polar. So oxygen is a little negative and hydrogen's a little positive. And what that means is that if I had another water molecule, the hydrogen is going to want to hang out near that oxygen. And then there's going to be an attractive force between those. So this yellow line will represent our cohesive force. Those water molecules want to be close to each other. Okay, so water wants to be near other water. All right, now let's go back to our sphere. Let's compare a water molecule in the center of the droplet. So let's say we'll look at a water molecule right here. So we'll represent that one with a purple dot. And then let's say that we have another water droplet that's right at the surface. So here we'll represent that one with a green dot. Now we'll represent other water molecules with blue dots. The purple one in the center of the droplet can have dots all the way around it, okay? Whereas the green one, because the air is there, can only have them about halfway around it, right? And that's because right here, there's air, right? So we have air at the surface of that droplet, and that minimizes the number of water molecules that my green droplet or my green water molecule can interact with. What that means is this is more stable. It's interacting with more water molecules, and that stabilizes it. It has tons more of those hydrogen bonds that keep it at a low energy. So which molecule is happier? Well, the one in the center of that sphere. And if at all possible, a water molecule would prefer to be at the center where its energy is lower. And so by adopting a round shape, it minimizes how many of those water molecules have to be at the surface. So by minimizing the surface area, it actually maximizes our cohesive forces. So minimizing the surface area maximizes cohesive forces. Maximizes cohesive forces. Okay, these cohesive forces have a pretty cool application, and that's called surface tension. You actually see surface tension anytime you see a water bug floating on the surface of a water. Think about what's happening here. We have this flat surface of water, and then when the water bug steps on it, he deforms it. And notice, really importantly, when it deforms, this one has a larger surface area. Larger surface area. And that means that there's more water molecules that used to be buried that are now having to come towards that air-water interface where they're less stable. So, cohesive forces result in this surface tension where I have to use a force to push down that water to pull those water molecules out of the center and let them come hang out at the surface. So what's surface area? Surface area is the force required to deform a liquid. And here we see this bug's leg coming down on the water. And if it wants to deform that water, it has to apply a force because more of these droplets then are going to be exposed to the air, and they're not going to be hanging out in the middle of water like they'd like to. So surface tension is the force required to deform a liquid. Here's the thing, water bugs can walk on water, but they couldn't walk on any old solution. Water has really strong intermolecular forces, which means it takes a lot of energy to deform that surface. Here's the thing about surface tension. Stronger intermolecular forces lead to higher surface tension. So because water has relatively high intermolecular forces, it's a good surface to try to walk on water bug style. But if you took another solution with lower intermolecular forces, then it would not be as easy for this water bug to walk on it. And some of them, if they had low enough intermolecular forces, it wouldn't be able to walk on at all. Okay, so that's cohesive forces and surface tension. We also said we talk about adhesive forces. Those are attractive forces between two separate substances. So here we see a paper towel dipped down into wine. And what we can see is that the red wine has been sucked up that paper towel, and it's going up the paper towel against the force of gravity. Why is that? Well, that's because there's attractive forces between the water molecule and the paper molecule. So notice, if we look closely at our little diagram over here, we got a water and a water and a water. Wine, by the way, is mostly water. It also has obviously other compounds in it, ethanol, for example, and there's an ethanol molecule. But all of these molecules are polar, and they're getting sucked up that paper towel, which also happens to be polar. So the polar wine really likes to be near the polar towel, and that's an attractive force that pulls it up. So it's the intermolecular forces that are responsible for this effect, where a napkin or a paper towel will suck up a liquid, okay? Now, if we compare the adhesive forces to our cohesive forces for different substances, we get interesting results. Let's compare our adhesive and cohesive forces. If we take a look here at mercury, that's just the metal Hg, it makes this sort of concave up shape right at the top. And next to it is glass, okay? And if we compare that with water, which we know is H2O, it makes this concave down shape. Okay, two different shapes. Why does it do that? Well, it all has to do with cohesive and adhesive forces. So the glass that it's interacting with, importantly, if we look at its molecular structure, is polar. And the water is polar as well. Meanwhile, mercury is nonpolar. What that means is that mercury would like to be near other mercury, those are cohesive forces, but it wouldn't like to be near the glass, the adhesive forces. So remember, adhesive is between two separate things, so that's what we're thinking about when we think about the glass and the substance in it. Cohesive forces is within a substance, so that's what we're thinking about when we think about just water or just mercury. So for mercury in glass, it would rather be near itself than near the glass. And what that means is that cohesive forces are greater than the adhesive forces. Meanwhile, for water in glass, the water would actually rather be next to the glass than itself. And so that means the cohesive forces are less than adhesive. And that's why we get this concave up versus concave down shape. Because here, this little segment between the surface and the peak of the water is extra surface area where that water can interact with the glass. Meanwhile, over on our mercury, by making the shape concave up there, it minimizes how much the mercury has to interact with the glass, okay? So cohesive versus adhesive forces give us these different behaviors of substances when we interact them with glass or with paper towels, etc. And one of the really important results of this is something called the capillary force. So the capillary action is the driving force for something to go up a thin, narrow glass tube. So when adhesive forces is stronger than cohesive forces, capillary action draws up the liquid in the narrow tube. And that's why we see this water being sucked up these tubes, because that water would like to be next to the glass. Meanwhile, if we look at the mercury, we see that there's actually capillary repulsion. What's happening there is that the mercury doesn't prefer to interact with the glass. And so rather than going higher than the surface of mercury, it's staying lower than the surface of mercury to minimize how much of that surface area there is that's interacting. So in this lesson, we've learned all about cohesive forces, adhesive forces, surface tension, and how they interact to result in capillary action.